I want to introduce Dr. Katz. So Sydney Katz is a postdoctoral researcher, as I said, at Stanford's Intelligent Systems Laboratory, which is run by Michael Kokendorfer. Her research focuses on the design and validation of safety-critical decision-making systems. And that work builds upon ideas from optimization, Bayesian inference, uncertainty quantification, neural network verification, and reachability analysis. She'll touch on a couple of those things today as she gives an overview of this idea of the validation of safety-critical systems. But overall, it is really exciting to have her join us to talk about this incredibly important and timely topic. So with that, I'm going to hand it over to Dr. Katz.
Awesome. All right. Thanks so much, Pax, for the introduction. So as Pax mentioned, my name is Sydney. I'm currently a postdoc here at Stanford. And my research, like you said, focuses on the design and validation of complex decision-making systems. And I'm super excited to have an opportunity today to talk to you all a little bit about what's been going on in the field of validation, specifically for these complex decision-making systems. And so to start out, I just want to talk about what a complex decision-making system actually is. So what does it mean when I say complex decision-making system? So in this case, a complex decision-making system, at least in kind of my lab and in our research, we often just refer to this as like any system that takes in kind of a lot of complex information and has to make a decision based off of it. So this could be like a self-driving car, it could be an autonomous aircraft, it could be a financial decision-making system. And then there's kind of this one category of complex decision-making systems that's become quite popular as of recent, and that is AI. So I would say AI systems also fit into this category of complex decision-making systems. In fact, they're quite complex. And I know the title of this webinar was AI safety. So for the purposes of this talk, if you want to just think of what I'm talking about as applying to AI, that's totally fine. You can just call it AI if you want. But in general, we're focused on kind of this just general broad category of complex decision-making systems, of which AI is part of. And kind of the key motivation behind everything that I'm going to talk about today is just that it's bad if these systems fail. And depending on where and how these systems are deployed, there's kind of varying degrees of how bad it is if they fail. So for example, if they're deployed in safety critical settings, so for example, healthcare, aviation, driving, it can be really, really bad if these things fail and result in quite catastrophic consequences. So for example, this could be like loss of property or even human life. And so really it should kind of come as no surprise that we really want to put in a very significant validation effort to ensure that these systems will behave as we intend them to when we go and deploy them in the real world. And it really is a significant effort because as I said, these are complex decision-making systems. If you think of an AI system, it's really hard to understand kind of the internals of what's going on and how it works, let alone when or if it might fail. And so it really requires kind of a significant effort of applying a number of principled techniques that people have created for validation to properly assess the safety of these systems before we deploy them. And in fact, there's actually so many different techniques and principles in this area that's actually possible to write a textbook just with these different ideas from validation. I know that because I actually was an author of one of these textbooks. And so I wrote this textbook called Algorithms for Validation with my PhD advisor and two of my lab mates. And then as Pax mentioned, we also turned that into a course here at Stanford, which you're welcome to enroll in online as well. And this book is actually the third book in a series of textbooks that my advisor has written. The other two books also have corresponding courses here at Stanford, and you can also enroll in them online. And all of these books are algorithms books, essentially. And the way that I kind of see all of these things fitting together is in the first couple books, we design stuff. So we design decision-making systems, we optimize them. Again, this could be like our self-driving car, it could be our aircraft, things like that, or a robot. And then once we're done with that, we can come over to this textbook or to my course, and we check if what we designed actually works. So we take that design for our system and we thoroughly validate it to check if it does what we intend it to do. And in general, we're focused on these complex decision-making systems, and typically we're very interested in decision-making systems that operate over time. So this could be like a robot, it could be a self-driving car, it could be an autonomous aircraft, a financial decision-making system, a healthcare system, For kind of the purposes of this talk, we're just going to wrap these all into one thing that we call the system, which is just the thing that we want to validate, the thing that we want to test. And this is one thing we have to define for our validation algorithms. There's one more input to validation algorithms, and that is the specification, which basically just says, what is it that we actually want our system to do, or what should it or should not do? So for example, for a self-driving car, maybe our specification is that the car should not collide with other vehicles on the road. And of course, you might have a variety of specifications for a given system. So you might have other specifications for the self-driving car that's like, don't collide with pedestrians or follow the road rules, like always stop at stop signs, things like that. But in general, given a system and a specification, we can pass these things over to what we call a validation algorithm, which takes in the system and specification and gives us some sort of information or kind of clues about whether the system satisfies its specification. So that could be something like a failure analysis. So what are scenarios where the system actually doesn't satisfy its specification? So in the self-driving car case, maybe we find scenarios that are very likely to lead to collision between vehicles. It could be formal guarantees. So sometimes actually under a set of assumptions, we can formally prove that a system will always satisfy its specification. So in the self-driving car case, maybe we can say like, for a given scenario where we kind of put bounds on what the behavior of other cars on the road might do, we can formally prove that we will never collide with another car on the road. It could also be an explanation. So it could be like, why did the system not satisfy the specification in this case? Or why did the system decide to make a particular decision? And then the last category has to do with when we deploy the system at runtime. We want to deploy these systems with runtime monitors to make sure that they're still behaving as intended, even while they're operating in the real world. And the way that I kind of see all of these different categories of techniques fitting together is described very well by this idea of a Swiss cheese model. So the way the Swiss cheese model works is that basically all of these different categories of techniques have limitations or like holes in them, kind of like the slices of Swiss cheese. But ideally, all these limitations or holes are not the same for each category of technique. So all these holes don't necessarily line up with one another. So if we were to stack enough slices of Swiss cheese together, ideally nothing can get through. So that's kind of the general idea here. And if you have like one key takeaway from this presentation, I hope it's this, which is that there's really no silver bullet in safety validation. So we can't just like take one of these techniques, apply it to our self-driving car, apply it to our large language model, and we're like, we're good to go. We can just go deploy this in the world. My formal method said I was good. Unfortunately, it's a little more complicated than that. And really what we need to do is kind of know the limitations of all of these different categories of techniques and stack a bunch of them together to build a safety case. So when we're talking about these really safety critical high stakes settings, it's really important for us to actually build a safety case. Okay, so for the rest of this presentation, I'm just going to go through kind of what these different categories of techniques look like so you can get kind of just scratch the surface flavor of what these different techniques might look like. So I'll start with the first technique, which is failure analysis. And to explain kind of what we deal with here and the types of challenges that we have for failure analysis, I'm going to use an example of aircraft collision avoidance. So here we're going to assume that we have this blue aircraft on the left, and it's trying to avoid colliding with this red aircraft on the right. And it has a collision avoidance system on board that's like telling it what to do to avoid colliding with the red aircraft. And our specification for this system is essentially just that we want to make sure that the blue aircraft doesn't enter within some region around the red aircraft, in which case we would call this a near mid-air collision. So in this case, the blue aircraft does not enter within this region, so we satisfied the specification here. But if we were to simulate the system again, we won't always get the same result because, we might have like sensor noise, different sensor noise. The pilot might not always respond in the same way. There's lots of other kind of environmental factors that can change from one simulation to another. And so it's possible that we could actually simulate the system and things don't go quite as well. And we get a simulation that looks like this, where we actually do have this near mid-air collision and we don't satisfy the specification. And so now what we want to think about, and what we often think about in scenarios like this, is something like, well, what is the probability that this happens? What is the probability of a near mid-air collision? And in general, when we're assessing these very safety critical systems, this is a really common question to ask, like, what is the probability of failure? And in fact, when we certify collision avoidance systems with the FAA, this is a question we have to do our best to be able to answer. What is the probability of a near midair collision? So to do this, you might think, okay, well, let's just simulate our system a whole bunch of times. Let's check out how many of them resulted in a near midair collision. In this case, it was 2 of them. So then we can just take our 2 near midair collisions that we had. We can divide by our total number of simulations. In this case, it was 60. And then we say, okay, so the probability of a near midair collision is around 0.033 or 3.3%. So this might be setting off like some alarm bells in your mind. I know it would be for me, because, you know, maybe if you have to fly in the next few weeks, like I sure hope that when I get on an aircraft, I don't have a 3.3% chance of colliding with another aircraft. In no worries, that's absolutely true. So the probability of a near midair collision for real aviation systems is much, much lower than 3.3%. And in fact, if we were actually to simulate a real aviation system, it would probably look something more like this, where we actually don't observe any near midair collisions in our simulations. So then you're like, okay, well, we got 0 near midair collisions. Let's divide that by our total number of simulations, and then our probability of collision is 0, right? But you know, if you're a little skeptical right now, you're quite correct to be skeptical, because that's not exactly true. Like the probability of collision is not necessarily 0. It's just that when we ran 60 simulations, that wasn't enough for us to actually find any near midair collisions. So then you might think, okay, well, that's fine. Let's just run a bunch more simulations so that we can actually figure out what the accurate probability of near midair collision is. And sometimes this solution is just fine, and this works quite well. People might call that like Monte Carlo analysis. But there are some problems here, because in some ways it's a good problem to have. But for safety critical systems, they're designed to be extremely safe already. So like aircraft collision avoidance systems are designed to have a probability of failure closer to like 1 in a million or even 1 in a billion. And if we have a probability of failure like that, it's going to require millions or even billions of simulations before we can actually observe enough failures to get an accurate estimate for the probability of failure. And you know, simulation is quite expensive, both in terms of time and computation. And so sometimes this is just completely intractable or infeasible to actually do, to be able to run that many simulations. So if you're thinking that, I'd come back to you and say, well, sorry, that's too expensive, and we need some other way to do this. And what we've stumbled upon right now is essentially the exact problem that we tend to focus quite a bit of our efforts on when we're thinking about failure analysis in our research. Because dealing with rare failure events is really the name of the game in failure analysis. Because these systems that are operating in high stakes settings, they're already designed to be very good at what they do. So their failures tend to be rare, but we still care about them because, you know, if self-driving cars are driving millions, billions of miles, it really matters that we understand all of the different edge cases that they might end up in. So we still care what they are, but they are very hard to find. And so there's lots of different methods that we work on in our research to kind of deal with this. Some of these methods rely quite fundamentally on this idea called importance sampling. So I'm going to give you kind of a preview of what that looks like today. And the way that importance sampling deals with this problem is we say, okay, so we didn't observe any failures when we simulated our real world environment, given our like limited simulation budget. So let's just simulate a different environment that we kind of like made up. It's like some synthetic environment, but we know that we'll actually observe some failures when we simulate this environment. So for example, maybe we could simulate the first environment that I showed you, where we actually did observe some near midair collisions. But you might be thinking to yourself, okay, that's silly though, because I don't care what the probability of failure is for this like made up synthetic environment. I want to know the probability of failure for the real world. But it turns out we can actually use simulations from this environment to give us an unbiased estimate of the failure probability for the real world environment. And the way that we do this is we actually re-weight all of the different trajectories that we saw in our simulation of this synthetic environment according to how likely they were to actually occur in the real world. So in this case, our 2 near midair collisions that we observed here, they were less likely to occur in the real world than in our synthetic environment. So they get a weight that's more like, instead of observing 2 near midair collisions, it's more like we observe something like maybe 0.15 near midair collisions in the real world. And then we can divide that by our total number of simulations. And then we get a new estimate for the failure probability that's non-zero now. In this case, it's around 0.25%. No worries, this is just like a notional example. For actual aviation systems, the failure probability is still much, much, much lower than that. But the key takeaway here is just that by reweighting these samples using these things called importance weights, we're able to actually get an accurate estimate for the failure probability. And if you're interested in learning more about exactly how these weights were calculated, so I just told you, you can kind of think of it as like reweighting according to how likely they were to occur in the real world. If you want to know the actual mathematics behind it, you can check out our textbook where we explain it in quite a bit of detail. But the key takeaway that I hope you have here is just that we were able to get a more accurate estimate of our failure probability using the same number of simulations that we used before. So we didn't have to increase our simulation budget, even though we had these rare failures that we needed to deal with. And in general, importance sampling allows us to efficiently estimate the probability that a rare event occurs. So lots of the different technologies and methods that we develop in the lab are kind of related to this idea of importance sampling. We also use different ideas in like optimization and other ideas in mathematics to help us deal with these rare failure events. And there's lots and lots of research out there that if you're interested, I would highly recommend you check out, both from our lab and many other labs around the world. We also discuss this quite extensively in the textbook and go through it in the class. So if you want to watch the lectures or enroll in the class, you'll also learn quite a bit more about this. Okay. So that was failure analysis. That's our first category of techniques. Some of the really nice things about failure analysis is a lot of the techniques I was just talking about are actually black box. So like we just need to be able to simulate the system. We just need to know like inputs and outputs, but we don't actually need to know like what's going on inside of the system for a lot of these techniques. So we don't need to know like what your system model is. We don't need to know exactly what the dynamics model is. As long as we can just call the simulator, we can still apply these techniques. So that makes them really universal to a lot of different problem domains, which is quite cool. The problem with failure analysis is that it doesn't give us any guarantees. So you might feel a little bit unsatisfied with the methods here because, you know, we can run failure analysis for a while. And let's say we run a failure analysis technique for a while and we don't find any failures. That doesn't give us a guarantee that the system will never fail. It's just that we didn't find them in our failure analysis. And so that might, you know, seem a little bit unsatisfactory to some of you. And so it turns out there's a way to fix this, which is to use formal methods to produce formal guarantees. And so the idea with formal guarantees is that sometimes we can actually guarantee that a system will not fail. But there's a caveat here, which is that we typically have to make some set of assumptions about the environment or other various factors that the system has relevant to it. So, for example, for our aircraft collision avoidance system, we might be able to say like, okay, let's actually bound, like we know, we bound the behavior of the pilot. So we know how quickly it will respond when we tell them to climb or descend, things like that. And let's like bound our sensor noise. So let's say that, you know, we can only be so wrong about our current altitude or something like that. And given all those different assumptions, we can actually calculate the set of states that are reachable for our collision avoidance system and kind of bound the set of possible trajectories that we might observe. And if we find that the set of possible trajectories doesn't include any trajectories that involve a near midair collision, then we can actually formally conclude that our system is safe given this set of assumptions. But kind of the key asterisk there is just that it's given that set of assumptions. So we had to make sometimes very strict assumptions to get these types of guarantees. There's also one more kind of caveat there with formal guarantees, which is that they tend to be much more computationally expensive. They're not black box like those failure analysis techniques I was talking about, so they require lots of knowledge about the internals of what's going on in the system. And they can grow quite computationally expensive as systems become bigger and bigger. So that's one caveat. But the nice thing is they actually give you a formal guarantee or a formal proof that your system will not fail, which is pretty cool. And just to kind of look inside a little bit at like what these different techniques actually look like and like what they're doing, I want to do a really simple example of formal methods that you can actually do hopefully in your head. So here's the idea. We have this like very simple domain here where it's just like the XY plane. And we know that we're somewhere in that purple square. So we're at one of the points inside of that purple square. And we also know that at the next time step, our X value is going to be increased by 2 and our y value is going to be increased by 1. So I want you to take a second really quick and think about, okay, if I start somewhere in this purple square, and I know that this is how my state will change at the next time step, where could I end up? What describes like the full set of states that I could end up in at the next time step, knowing that I started somewhere in the purple square? So think about that for like 10 seconds or so while I drink some water. Okay, and so hopefully you did maybe some math in your head. And maybe it looked something like this, where you imagined kind of taking this square, you imagine taking all of the points in that square and moving them to the right 2 for the x position, and then you imagined moving it up 1, and then you got this like new square, and this is the new set of states that we could be in at the next time step. And so this is essentially all that formal methods do. It's just that typically the equations are much more complicated, and it's not something we can just do in our heads like this. And so we rely on some more advanced techniques in mathematics to actually do this. But one thing that's really cool is as we develop these techniques to kind of understand how inputs affect the output of these various, or like input sets can be propagated to the output of these various formulas, we can actually do some really cool things. So for example, a neural network is also just a mathematical formula. So we can take a lot of these different mathematical techniques and actually use them to understand how a neural network processes various inputs. So for example, here's like a mathematical formula that represents a very small neural network. And we could actually take this formula, apply some math to it, similar to the math you did in your head, but a little bit more principled so that a computer can do it instead, because this formula is a little more complicated, at least for me, than I could do in my head. But what we can do is when we apply this math, we can understand the set of possible outputs for this neural network. So you could imagine that that could be quite powerful, because we could say, like, given this full set of inputs for our network, I know exactly what outputs are possible. So say I had a neural network that was like deciding aircraft collision avoidance maneuvers. I could say, for all of these different states where like the one aircraft is above the other aircraft, I know for a fact that it will tell the other aircraft to descend or something like that. And that can be a really, really nice proof or guarantee to have, especially given the complexity of these different machine learning models. So if that sounds interesting to you, the kind of field or keyword to look up is neural network verification. My lab wrote a survey paper on the topic a number of years ago, and I also made an introductory YouTube video on the topic if you're interested in checking it out. But these neural network verification tools have been developed over the last like 7 or 8 years, and they continue to get better and be able to scale to larger and larger networks. And so I think it's a really exciting field that you can check out related to formal guarantees. Okay, so that was our second category of techniques. Now I'm going to move on to the third category, which is explanations. And so the different ideas that we talk about related to explanations in the book and in the course are kind of related to a number of different things. One is like policy visualization. So can we just visualize what decisions our system makes for various inputs and use that to understand exactly how it's behaving? A lot of visual tools are very useful for this. We do things like sensitivity analysis, which is quite popular in explainability. So for example, we can figure out like what disturbances or what noise values contributed most to like a failure of a system, for example. Or it's quite popular in explainability for like computer vision systems to understand, you know, like what pixels in the image were most important to the prediction that the model is making. And then finally, we also talk about failure mode characterization. So relating back to the failure analysis categories of techniques, like maybe we got a whole bunch of failures from our failure analysis, and now we just need to decide like what to make of it. Like, do these failures matter? Should we incorporate some kind of mitigation to them in our next round of design for the system? And we want to be able to answer that question. And so there's a number of techniques we can use to kind of group those different failures and try to understand what it is that's causing them and like how they relate to one another. So those are different techniques we talk about in the book. There's also kind of an up-and-coming field in explainability that I'm particularly excited about right now. It's a little bit newer, so we don't actually cover it too much in the textbook, but I want to talk about it just briefly here by introducing it with kind of an example. And so here's one example where let's say that we were, so this is actually a picture of a taxiway or a runway that an aircraft would be taxiing down. And let's say that it had like a camera on it and we were using this camera to like steer ourselves down the taxiway. So since, you know, I don't know how many pilots we have here, but if not, you can just relate to like, let's say we were just driving down the taxiway and we wanted to like keep our car near the center line. And so then you might be able to say like, okay, let's say that you saw this image, and to safely taxi down this runway, we want to make sure that we know where we are in relation to the center line. And so you might look at this and say like, okay, well, what features of the image would you focus on to determine how far you are from the center line? So think about that for maybe like 5 seconds or so. It's really not a trick question. Okay, so I'll just answer for myself. If I were looking at this image and I wanted to figure out where I was on the runway, I would probably look at the 2 edge lines, and then I would look at the center line. Okay, so not a trick question. Okay, now let's imagine we have a very similar image, but now it's like a different time of day, so the sun's actually at kind of like a different angle, and like the aircraft is like casting a shadow on the runway. So now think about it for like a couple seconds. What features would you use to figure out where you are on the runway? Okay, and again, I'll just answer for myself. I would use the same features. And particularly, I would not use the shadow to figure out where I am on the runway. And in fact, if you did tell me that you were using the shadow to figure out where you are, I probably wouldn't get on that plane with you, or I probably wouldn't get in the car, because this is not really a reliable feature for us to use to figure out where we are. And so I think what we want to be able to do is actually ask similar questions like this to our AI systems, because if we can understand the AI system's answer for this question, we have the potential to understand a lot more about its behavior and like potentially put more trust in it. And it turns out with some recent new techniques and explainability, we can actually do this. We can actually answer these questions. So for example, let's look at this image here. The first question that we can ask is, what does the AI see, or what does the machine learning model see when it looks at this image? And we can actually highlight kind of the top 9 features that it sees in this image by looking at just like summary similar images for these different features. And so you can see that actually like 8 of the top 9 features kind of correspond to this like idea of a shadow. So all of these different features, when we look at their summary images, they have like some form of a shadow in them. But then if we look at that 9th feature on the bottom, it actually corresponds to the right edge line. And so you can see it's actually corresponding to what I would consider a more robust feature, which is one of those edge lines. But looking at all of this, I think I would be a little bit concerned, because I would be like, oh no, the AI is seeing mostly shadows. Like that's mostly what it's focusing on, is the shadow. But that's not actually the question we're asking. We're just asking the AI, what does it see? But we can actually ask the question, what is it using for the task of figuring out where it is on the runway? So in other words, what is the AI system focusing on specifically for this task? And it turns out if we answer this question using our various explainability techniques, we can see that it's actually mostly focusing on that 9th feature on the edge line. And it's putting very little weight on those features that have to do with a shadow. So this can give us a lot more confidence in the system, because we can say, not only does it know that there's a shadow there, it also knows not to focus on it. And so I think this is like a really powerful piece of information to have for a safety case when we're looking at these systems. And so I'm really excited about where this field is going. The way that we can answer these questions is using a new idea called mechanistic interpretability. This has really become popular in relation to large language models, but it's kind of percolating into lots of other parts of AI as well, because what it allows you to do is kind of understand the different processing that's going on inside of these large transformer models. So I'm really excited about where this is going. I think it has a lot of potential to help us build safety cases for these systems. So if you're interested, those are kind of the keywords to look up, which would be mechanistic interpretability. All right, so that's 3 of the 4 categories. And what the first 3 categories that I just showed you have in common is that they're basically all things that I would consider to be offline methods. So these are things that we would apply before we actually deploy the system in the real world. So for example, like failure analysis, formal guarantees, these are all things that we would do and analyze and then have a good idea of before we actually go deploy our system in the world. And one kind of key feature of all these methods is that they require a number of assumptions. So for formal guarantees, we talked about it quite explicitly. They require a lot of different assumptions to actually kind of get these formal proofs. But in general, for all these other methods, we still needed like some model of the world. We still needed a model of all of the different things that might happen. And, it can be really hard to build these models. This is like an extremely time-consuming part of building a safety case, is kind of modeling the world. And inevitably, we're going to miss stuff because we have to make all these assumptions. We have to make this model of these very complex environments. And we're probably never going to be able to get it all right. And so what I think can help us here is this idea of runtime assurances. So as I was saying, we do our best to model the world using offline validation. So when we apply all of our failure analysis, et cetera, but we're just inevitably going to miss stuff, especially as we talk about deploying these complex systems in complex environments. So for example, the roadways. So these are two examples here. Here's like an edge case that a Waymo vehicle encountered in San Francisco, where I think like a fire hydrant or something kind of exploded, and there's like huge amounts of water just shooting straight up from the street. Not something that's easy to think of when you're modeling the world for a simulator, for example. And then on the right is another edge case for a Tesla, where the moon was positioned in such a way that it just had this kind of coloration and position in the sky that made it look just like a yellow light. And so this Tesla basically just kept slowing down because it was actually detecting it as a yellow light, which is, again, not something that's easy to think about as you're building your safety case. Like, oh, what if the moon is at this position and kind of looks yellow? It's not something that's like super obvious to think about. And so these are the types of things that kind of like keep safety engineers up at night, I think. And during my PhD, it was always something that kind of bummed me out because I was like, man, I'm trying to do all this stuff to like help build safety cases for these systems, but like we're always going to miss stuff. Like what are we ever going to do about this? And I think a lot of people agree with me. Oh, I think maybe this slide is not true. Okay. I think a lot of people agree with me because basically every time I give one of these talks, I get at least one question that's something like, how can I capture all of the different scenarios that my like crazy complex system is going to end up in? I don't even know what they all are. And I agree, and I typically will reply and say like, yeah, it's a problem, kind of a bummer, but I think there is some hope here, which is that we can do some runtime monitoring. So people have been working on lots of techniques over the last several years in order to be able to check when a system is in a situation that it didn't plan for or that it didn't validate for offline or wasn't in its training. And so what we can do is we can try to flag these scenarios that we didn't train or validate for at runtime before they cause potential danger. So you can think of like that Waymo vehicle, for example, like flagging that it's in an uncertain situation and transferring control back to a remote operator. Or in general, a lot of these different systems have kind of backup safe modes that they can enter if they're in an uncertain scenario. So, we will always inevitably miss stuff in our offline validation. But I think runtime monitoring is a good way to provide that kind of last layer of the Swiss cheese model to catch everything that we missed in those other parts of the safety case. So that's kind of the general idea of all of these four methods. What I went through today like really only scratches the surface of all of the different stuff that's out there. But I hope that it's kind of piqued your interest so that you're maybe interested at least in learning a little bit more. And if you want to learn more, again, there's lots of links for you. So there's the textbook, all my lectures are online. You're welcome to take the course as well. I would love to see you there. And in general, it's just important to kind of stack all of these different methods together in a safety case. So I hope that's the key takeaway you have here. And then here's just a bunch more links. If you're interested, that's actually a link to the course webpage. And I'm really looking forward to hearing all of the questions that you have.
Thank you so much, Sydney. That was fantastic. We do have a couple questions that came in, so please continue to ask them, and we'll get to as many as we can right now. So I think, Sydney, maybe we had a question come in earlier when you were, I think, talking about the failure analysis, or actually, I guess it comes to the very beginning of kind of when you're building out, when you're thinking about building a safety case. How do you know that your specification is sufficiently complete? And if not, how do you address incompleteness? I mean, I guess, how do you define, what is safe behavior in that sense?
Yeah, that's a great question, especially for these systems that are like operating in these very complex environments. I don't know if there's any great way to necessarily ensure that it's complete. My recommendation would be like come up with as many specifications as you can and try to run these different failure analysis techniques against many of them. I will also say that it's possible that you can do like sometimes some sensitivity analysis. So like if you know that, maybe you're like, oh, I want it to come, I don't want my self-driving car to come within like 10 feet of another car. But then it turns out that it's very sensitive to that threshold. Then you know that it's really important to get that specification right. Versus if it's not very sensitive, then you can say, okay, well, I had a specification and it was probably enough, because if we were slightly wrong about it, then our analysis doesn't change too much. But I think in general, it's a very difficult problem and requires typically a lot of domain knowledge in whatever particular field you're applying it.
And I suppose this also comes back to your point about the runtime analysis, right? You can never anticipate everything that might happen, and that's why you need to continue to monitor the systems. Exactly. So we've got a lot more coming in here. So let me see if I can get a good, maybe just coming back to the beginning again and starting at the high level recent question. Now, these failure analysis, these refer to, can you come back to your beginning? You said these apply to any decision-making system, but you can call it AI. Can you expand on that? So the specific question is, do these systems refer primarily to neural networks or any kind of machine learning, AI, LLM, any kind of what we might call intelligent system or AI system?
Yeah, so the short answer is yes, it applies to anything. Longer answer is it depends a little bit. So the failure analysis techniques, the reason I love them so much is a lot of them are black box. So it doesn't matter what's under the hood. It could be a neural network. It could be a very complex control system. It could be some large rule-based system that's got a bunch of if-then statements. It doesn't matter. We just need to be able to like query the system. Formal guarantees, because they require access to like the internal of the model, it actually does matter what the system is. But as I kind of mentioned, there are formal guarantees for neural networks. So we have been making progress on how to actually get these guarantees for neural networks. I wouldn't say they necessarily scale to like ChatGPT size networks. But in that case, I think there's even a lot more work there, which kind of goes back to like, how do you know you have the right specification? For large language models and these kind of really messy environments, it's like really hard to figure out what that is. Like, how do I say that I never want my language model to like say any hate speech or something like that? It's very hard to like mathematically write down what that specification is and then formally prove it. So I think that's kind of just a long-winded way of saying like, we design these methods to be quite general, to apply to lots of different types of decision-making systems. But the more you know about your system, kind of the more in the weeds you can get and more specific you can get to like the exact system that you're trying to use.
That's great. And maybe building on that, there are a lot of questions kind of about the relationship to some of these techniques and humans. So going beyond kind of the algorithmic validation, how are people, including end users, involved in this AI validation, this validation of the decision-making systems? How do you account for it? And I will say, I think it's on the CISL lab, the Intelligent Systems Laboratory, but I remember you did simulations of likely rare events of where a car could have a collision. And one of them was just a person running into the car. And it was hilarious. And then there was in the news, like a few days later, like people actually doing that. So it was a kind of an interesting case of the model, preceding the reality. So, yeah, how do you take account for humans as end users or as people interacting with these systems?
Yeah, that's also a great question. So I think I'll go first to aviation, which is a field that my lab has a lot of experience in, specifically like working with the FAA, for example. And when you design a system like the collision avoidance system that I was using as an example, you have a ton of stakeholders. So you have like the companies that will be putting this on their aircraft. You have the end users that are going to be flying on the plane. You have the FAA who's responsible for giving it a stamp and saying like, yes, this is safe. And you have to be able to really like communicate all of these different ideas to the people and these different end users. And there's lots of different ways to do that. Specifically working back and forth with like the FAA, for example, we actually were able to work with them to understand like, what is the specification that they have? Like, what do they care about for the system? For example, they cared a lot about like, what is the probability of failure? But they also cared about like, what is the probability that it's going to alert a whole bunch? Because if it alerts all the time, then these pilots are going to start to ignore it and it's going to become a nuisance to them. And so you don't want that either. And so I think it's really just making sure that as you build the safety case, which is something that I didn't quite touch on a ton in this presentation, but it's really an ongoing process where you're kind of iterating between all of the various stakeholders that care about the safety case that you're building, and understanding that both taking feedback from them to incorporate it into like your models and your specifications, but also like communicating your results to them so that they can build trust in the system.
We got an interesting question related to that is how do you see this evolving as, if we go back to the 3 textbooks, as artificial intelligence or complex algorithms are used more and more to design systems, how do you see that influencing, or will that influence the way that we need to validate these systems? I mean, is it going to create more unexpected outcomes, or I'll leave it at that.
Yeah, I mean, as these systems get more complex, the validation gets more complex as well. They kind of develop together in some ways. And, I think for these more traditional forms of automation, it's much easier to build a safety case around them, or maybe I won't say easier, but more well-established. And now that these new techniques are coming in, where we have these data-driven models specifically, it's quite difficult to build a safety case for them because we don't have necessarily like traditional math that we can rely on. So for example, like traditional control theory, it like typically comes with proofs, and we know that it will work. These AI systems, they don't come with that similar guarantee. And a lot of times we actually need like a similar data-driven approach to do the validation that we needed to actually design the system. And that's something new, especially for like regulators and stakeholders. They're not very used to that type of a safety case. And so there's kind of a lot to still be done to make sure that we're doing this properly.
And maybe that builds on or begins to answer a related question, is just, to the extent that we're always testing, right? There's runtime monitoring. There are always going to be edge cases, things that are unexpected. The environment, the other systems they're interacting with are changing. How do we know when a system is validated enough to be to go out there in the wild? And I assume that's maybe not an engineering decision. That's maybe a policy decision. But what are your thoughts?
Yeah, it is kind of the $1 million question there, I would say. It very much depends on the industry you're in. So, for example, in aviation, it's actually somewhat clear, clear in that you need to get your thing certified before you can deploy it. How you go about getting it certified is also still quite messy and not necessarily clear, especially for these more complex systems. But I think it's really hard to draw that line, and it's going to have to be a lot of domain experts that ultimately make that final decision. And you're kind of right. It's not necessarily an engineering question. I hope, I've provided a lot of information, and we have lots of tools to do the best that we can. And at the end of the day, someone's going to have to make that decision.
And building on that and related to it, how do you know, so you mentioned, for instance, when you do the simulations and then you reweight the probabilities based on what it sounded like was real world data. How do you know that a system isn't overfitting when you're doing some of these failure analysis? Isn't just overfitting the model that you're using, the simulator, versus real world circumstances? What are some of the ways that you test for that? Or is that part of what building the whole safety case is about?
Yeah, that's a super great question. First of all, you should validate the model that you're using. So not only do you want to do validation using the model, but you need to validate the model itself. So I keep going back to this collision avoidance example, but it's an example of a very successful autonomous system that's kind of gotten certified. And they had this model of all of these different ways that aircraft could approach each other in the airspace. And they actually got that model from 9 months of radar data covering much of the continental United States. And then they were able to take that model and run simulations using it and validate that it actually matches the real world data that we see in the real world. So that's one thing. You got to prove that your model is actually correct. The next thing that you can do is kind of something I mentioned earlier, which is sensitivity analysis. So let's say we were maybe slightly wrong about one of our model parameters. We can check what effect it would have if we were kind of wrong about it. And if we're very wrong about it, then maybe we need to do a little more analysis to make sure that we're really getting that parameter right. But if it doesn't matter so much if we were wrong about it, then we can feel a little bit more confident that no matter what model we're using, our results are somewhat accurate and we can trust them. And then the final thing is kind of like runtime monitoring. So if the model that we had when we trained and validated isn't matching what we see in the real world, that's something we definitely want to flag. And so that's why we want to deploy these systems with runtime monitors.
You touched on this with failure analysis, but when you have you have real world data on things that happen, but there are very, very rare events. How do you test for those rare events? I mean, with the simulation, again, you touched on this failure analysis. If it'd be 10 million simulations before this rare event would occur. How do you test for those and sort of push on the boundaries of the safeties of these systems when it comes to very rare events?
Yeah, so one thing you can do that we take advantage of quite a bit is using optimization. So we can know that we're getting kind of close to finding a rare failure event. So maybe like we simulated a scenario, we changed up some of the different sensor noises and different configurations, and we found that it came very close to a collision. And so then we can kind of pull on those strings a little bit more in a principled way using optimization techniques to get us closer and closer until we finally do find a scenario where we actually have a failure. So in a lot of ways, it's a coverage problem. There's so many different scenarios that we can simulate or try out, and we just don't have time to try them all. And so we need to rely on various cues and kind of sometimes build up our own internal models of like where we think things are likely to fail so that we can devote our testing to these areas that we think are more likely to cause failure.
We're running close to the time here, so maybe just two more questions. You mentioned mechanistic interpretability use in LLMs. Is that true? And could you provide some more details about what that involves?
Or yeah, sure. So it's mostly, so it's mostly been developed for LLMs, but you can apply it to really any like large transformer model. And the general ideas behind it is to just understand the actual like internal mechanisms that are going on in these machine learning models. So one very common way to do this is to take like an embedding, so some internal state of the model, and try to disentangle all of the different concepts that are present in that embedding. So for example, maybe you feed a sentence through this model that's like the dog went for a walk, and then you try to disentangle all of the concepts it's looking at. And maybe it's thinking about the outdoors, and you find out it's thinking about animals and specifically dogs and things like that. And you can actually understand that those are the concepts that are lighting up when you feed these things in. And that allows you to really understand kind of like what these models are doing. So in a more safety critical setting, or maybe just high stakes setting, you could think of like maybe like a loan approval system. And you give, an LLM a whole background on someone, and you say like, what should we approve this loan? And then you can understand and look at the different features that are going on inside the model and see if like maybe certain protected characteristics are lighting up, because you don't want it to be relying on those features to decide whether or not to approve the loan. And so these are different ways that you could actually like put more trust into the system if you can understand what it's thinking about when it makes its decision.
Great. And maybe one other question that came in a little bit earlier is, you're talking about using these systems primarily for deploying them out into the wild, right? Something like a car or something like that. But can you use these earlier? Are these applicable earlier? So for instance, if even when you're at the stage of training a system where you may be dealing with sensitive data and you want to understand how the risks there involved in training on the sensitive data, I mean, do these apply there? So for instance, if the specification was making sure it's anonymized, the context here being something like healthcare, is that something, are you seeing these kinds of safety cases applied and developed earlier in the process around training or earlier points?
Yeah, absolutely. And, sometimes it's easy to think of it as kind of a linear process where, you design your system, you do some safety validation, and then you go deploy it in the real world. But we actually talk about kind of in the introduction to the book as well that this really is a cyclical process. So like you'll design your system, you'll do some validation, you'll look at those results, and you'll go back and redesign quite a few times. So, when we were doing this aircraft collision avoidance system, we'd have intermediate designs of the system, run the full validation cycle, present our results to the stakeholder, take all that feedback, and redesign. So it is really a continuous cyclical process.
That's wonderful. With that, I'm going to just remind everyone that there are a lot more resources that are available if you're interested in learning more from Dr. Katz. So there's a link right there, a QR code that you can go to get more links to other papers and resources that Dr. Katz has provided. Your website, as well as the homepage for the course that you're teaching in the winter. In your interface as well, you can see additional resources, including links to the entire lecture series. So if you're interested in not just scratching the surface, but digging into more detail, you can find that link to all of those lectures. Again, if you're interested and qualified, you're welcome to apply to take the course as well here as an online student while she's teaching it on campus to other Stanford students. So really wonderful opportunity to learn more about this. We know this is a very important topic. Sydney, thank you again for joining us. Is there anything else you would want to add, or any other plugs that you would want to make in terms of people or resources that they can refer to as people are thinking about this important topic?
I think you pretty much covered it. I just want to say thanks to everyone who made it today or watched this after the fact. I'm really happy to be able to share all this.
Thank you. And thank everyone again. We will be sending out a recording. So if you missed it, or you had to hop off, or you have a friend who might benefit from it, we will be sending the recording out. Thank you, everyone.